It's recording now, and I will share the screen. Cool. So, first thing is first, we'll work through some revision questions. Cool. So, what formula best describes the relationship between phase and line voltage in star? Checking you guys are able to hear me. So yeah, what formula describes the relationship between phase and line voltage in star? Cool. So this is just something to be just getting our brain started. So yeah, the relationship between phase and line voltage in star is square root of 3. So to get line voltage, we multiply the phase voltage by square root of 3. And to find our phase voltage, we divide our line voltage by square root of 3. So in star, line current is equal to line or phase voltage. So number 2 in star, line current is equal to line or phase voltage. Okay. Yeah. So guys, these are just some revision questions. So just working through them just to kind of blow the cobwebs out from last term. So, yeah. Cool. So how about this one? Question 9. Can three single-phase transformers be used instead of a dedicated three-phase transformer? Good. Someone's responding. Yep. So yes, we can use three single-phase transformers instead of a dedicated three-phase transformer. It's what we do for the transformers here at ETCO. Well, I guess I should say I'm not technically at Wellington ETCO. I'm here in Auckland, just for 2 weeks. But obviously it's less efficient having three single-phase transformers. Cool. So what are the main two methods of cooling transformers? The two main methods are oil and air. Yeah, so most oil-filled transformers, you rely on natural air convection to help radiate that heat out. And then we also have forced air. So when you guys go and watch the video of this later, you can have a go at some of these questions. But for now, we will get stuck in to topic for tonight, which is electronics. So now we're starting to move on to electronics. So all of term 4 is done about electronics and protecting electronics. And then we'll do revision as we get to the end of the term, because you guys will obviously have your capstone at the end. And I will send out some practice capstones towards the end of the term, and then we will go through the answers during night class. Cool. So electronic components. So circuits are made up of a number of different components, such as capacitors, resistors, and diodes. Components can be grouped into two main components, passive and active. So most electronic circuits can be simplified down into multiple stages, each made of 2 or 3 components. So passive components do not contain a semiconductor. Active components contain a semiconductor. So you would consider a diode an active component, whereas a resistor would be a passive component. Cool. So resistors. So the main purpose of resistors are to limit current and dissipate power. So they're rated in ohms, as most of you guys will know, and the maximum power dissipated rating is in watts. So they're a passive two-leg component used to limit current or set voltage levels in circuits. So they come in preferred values, so 1 to 1.2, 1.5, 1.8, 2.2, 2.7, 3.3, so on and so forth. And maximum power dissipation determines component size. So if we look at the picture, there's 6 to the left are quarter watt carbon. The next 2, so got 1, 2, 3, 4, 5, 6. So they're 1/4 watt carbon. The next 2 here and here are half watt carbon, and then the last 2 are 4 watt and 5 watt wire wound resistors. So generally, the bigger the resistor, the more power it's able to dissipate. Cool. So your typical applications are reducing current flow, adjusting signal levels for other devices, dividing voltages in terms of series, used to bias an active component, terminate signal lines, and terminate transmission lines. So higher power resistors can be made to dissipate several kilowatts of heat. They can be used for motor controllers, power distribution systems, or as test loads for generators. So you can hook up a big resistor to test a generator to see how much power it's generating based on the known resistance, voltage, and current. A fixed resistor has a resistance that changes only slightly with temperature, time, or operating voltage. This is called its tolerance. And then we have what we call a potentiometer. It is an adjustable voltage divider. So it's really used to dissipate power. So they're made of thin carbon film with a wiper connected to a shaft, which provides the middle terminal. As a three-leg device, it becomes an adjustable voltage divider. If only 2 pins are used, it becomes a variable resistor. So variable resistors can be used to adjust circuit elements such as volume control or a light dimmer, old school light dimmer. They operate by a mechanism, can be used as a position transducer for a joystick or throttle position sensor. The thin carbon film that makes up the mechanism cannot dissipate any meaningful amount of power, so a potentiometer is usually used to control the output stage of a circuit. They may come in double gang or triple gang versions, which provide multiple potentiometers on the same mechanical shaft. This allows the potentiometer to control 2 circuits at once, such as the left and right channels of a stereo audio amplifier. So have you ever looked at old school stereos and amplifiers with the knobs that used for the volume control? They're actually potentiometers. They're often commonly referred to as pots. So if you ever have to replace them, general term for them is called pots, especially when you work in the kind of live audio with old school amplifiers and valve amps. Cool. Semiconductor diodes. So these are devices that only allow current to flow in one direction. Arrow points in the direction of current flow. So these are used to control which way voltage can flow and which way it can't. So it's a 2-terminal component that only allows current to flow in one direction, has a low resistance in one direction and very high resistance in the other direction. It's made from crystal of semiconductor, usually silicon, and like you may have talked about before in year 1, half doped P-type and the other doped N-type. A wire is connected to each side of that junction. So most of them have a stripe marked on one side to indicate polarity. The line indicates the cathode. The cathode is the negative side, the anode, the positive side. I got that the wrong way. When the rated reverse voltage is exceeded, a diode will eventually begin conducting. This point is called reverse breakdown voltage. The electronics topic is unfortunately quite dry. It's just the way it is. We do have to learn about it because it does form part of your capstone and then possibly also your theory exam once you get to next year. Cool. So application. So rectification, preventing back current, protecting from back EMF or polarity protection. So what is rectification? What do you guys know about rectification? So when we talk about rectification, we're talking about transferring AC to DC. So we're rectifying the AC signal into a DC signal. More often than not, you have, when you rectify an AC circuit, you get rippling DC, which then will look at other devices that smooth it out. So why would we want to prevent back current? Yeah. So if we're running a single device off two separate suppliers, it prevents current traveling back up from the supplier that is off. Parallel power supplies bypass switch. Um, so why would we need to protect something from back EMF? What could cause back EMF? Anyone think of anything that could cause a back EMF? Yes. Yeah, that's a good one, Leighton. So, yep. So a motor or any form of inductive load, so a motor, transformer, elements, so anything that has an inductive load um, on DC could, so like a relay coil driver, could induce a back EMF when we turn it off because of the collapsing magnetic field. And so that back EMF could damage the power supply. And then polarity protection. It prevents damage to a DC device from incorrect polarity. So a diode can be placed immediately after the input terminals. So the DC device, if you accidentally hook it up backwards, the diode will stop any damage. The device won't work, but it'll stop it from being damaged. Cool. So you've got different types of diodes. So power diode, they're used for rectification, polarity protection, or back EMF protection. You've got your signal diodes. They're smaller that react well at high frequencies that power diodes are not designed to handle. Got LEDs. So we all know they're a diode that emit light. Avalanche diodes, they're manufactured to conduct current in reverse above a certain voltage. So once a high enough reverse voltage is applied, an avalanche diode suddenly begins conducting with little voltage drop across it. It's used to protect from high voltage spikes. Your Zener diode, they're like an avalanche diode in that they're designed to conduct in reverse above a certain voltage, but they're manufactured to maintain a very precise reverse breakdown voltage. By intentionally placing a Zener diode in reverse, it can be used to give a reference voltage, which could be used to drive a voltage regulator. Oh, and then capacitors. So we studied a bit about capacitance in previous topics, especially with the AC theory, which you guys would have done in term two. Um, Yeah, unfortunately, it's the electronics should have been, in my view, it should be taught at the same time, but I don't decide the schedule. So it's a passive two-terminal component, and it stores potential energy. So it was originally known as a condenser. A capacitor stores potential energy in an electric field. So the physical form and construction of a capacitor varies depending on the application, but generally they're made of two plates separated by a dielectric. So the most common material varied is the dielectric itself. They may include glass, mica, ceramic, plastic films such as polyester, polystyrene, paper, air, or oxides of various types of metal. So who can tell me what a dielectric is? Not what type of material, but what a dielectric is. So that's the capacitor is the what stores energy, but a dielectric is something else. Does anyone want to take a guess? So it's a insulator or very poor conductor, but it is very, very thin. So when it's placed in an electric field, it's so thin that it almost conducts. So the electrons get fooled into thinking it can pass through it. So that's how we build up a charge on either plate, is because the electrons think it's a short circuit, but they can't actually get through there. Cool. So your types of capacitors. So you've got your ceramic, which is the one at the top, mylar, electrolytic, and tantalum. So ceramic capacitors can handle high voltages. They're also very cheap and have low capacitance. So they're not very high in capacitance. So they're normally used for temperature compensation circuits and also extensively in both noise suppression and radio circuitry. Your Mylar capacitors, also known as green caps, because they are always pretty much green, uh, they're relatively cheap and their general purpose non-polar capacitor for electronic circuits. So when I say non-polar, as in non-polarized, electrolytic capacitors are probably what you're used to seeing. And they're used for smoothing or rectified DC, and are also used where high capacitance and small physical size is required. So those are the types of capacitors you normally see in your computers. If you've opened up a computer circuitry, you'll normally see those types of capacitors. And then your tantalum capacitors have very high temperature stability. So they're very good at maintaining their capacitance at high temperature. Cool. So your application, so energy storage. So they act like a fast charge discharge battery. So good for car audio. Um, Power conditioning. So they're used to smooth the DC output of a rectifier and can also be used to store energy in a charge pump circuit. So a flyback converter. So the power conditioning. So when we use the diodes to rectify AC to DC, it comes out as pulsating or lumpy DC. As we pass it through the capacitor, as the voltage goes up and down, the capacitor charges and discharges, but it also allows a certain amount of voltage to pass or current to pass through. So instead of it coming up and down, it starts to get smoother and smoother as we put it through capacitors and other smoothing devices. So we use it for DC circuit smoothing. Power factor correction. So you guys will have talked about in your AC theory correcting bad power factor using capacitors or inductors, depending on whether your circuit is capacitive or inductive. So they provide leading VARs to cancel out the lagging VARs produced by motors and transformers, which is why a lot of single phase motors, like we looked at last term, end up being cap start, cap run. Because they also kind of smooth out that voltage and current so that it is a better power factor. Signal coupling. So as a capacitor blocks DC, it can be used to separate the AC and DC components of a signal. So for example, satellite dish. And decoupling. So it protects one part of a circuit from the effects of another. Noise caused by other circuit elements is shunted through the capacitor, reducing the effect the noise has on the rest of the circuit, which is very important in things like telecommunications and Wi-Fi. Cool. So transistor. So it's a semiconductor device used to amplify or switch signals. So who's heard of a transistor before? Where have you heard about transistors? What's the oldest reference you've heard about transistors, or where have you come across them before? Yep, good old transistor radios. Yep. So it controls a big current with a little current. So current flowing through the base allows the current to flow from the collector to the emitter. So the amount of current can flow is determined by the gain, HFE, multiplied by the base current. So in this example, a 6 microamp flows into the base, allowing 60 milliamps to flow through the collector. The BC548 transistor used has a gain of 100. So if we multiply the 6 microamp by 100, we get 60 milliamps. So applications. So we can use them as a switch, amplifier, or as a Darlington pair. So a switch, so pick a small enough resistor for the. Yeah, it's basically just a switch. But as an amplifier, so yeah, a Darlington pair. So a transistor fed into another transistor means the gains are multiplied. This allows an incredibly small amount of current to drive a load. Cool. Voltage regulators. So a voltage regulator provides a stable DC voltage regardless of the load current, temperature, and line voltage variance. So a 7-8XX range of voltage regulators are positive voltage regulators. This means they will supply voltage in a positive bias at a rated voltage. Therefore, a 7812 voltage regulator will regulate a positive voltage of 12 volts, regardless of voltage spikes. It is a fixed 12-volt output voltage. The input voltage should lie in between 14.5 to 27 volts. to allow the voltage regulator to do its job. So protection circuits against a short circuit and thermal overload are incorporated inside this integrated circuit. The safe area protection is provided for output transistors. So that's the 78XX range. So the 7812, 7824, etc., etc. But a 79, so with 78 is positive, 79 range of voltage regulators are negative voltage regulators. It means they supply voltage in a negative bias at a rated voltage. So therefore, a 7912 voltage regulator will regulate a negative voltage of 12 volts. So it's got a fixed output of negative 12 volts. The input voltage is similar. It should be anywhere from negative 27 to negative 14.5 volts. And protection circuits against short circuits and thermal overloads are incorporated into it. Safe error protection is provided for an output transformer. So to put it in perspective, that photo, that component would fit on the black part would fit on the end of your finger. So that's the size of it. Cool. So some common terms. So you got tolerance, preferred values, stability, power rating, voltage rating, and a current rating. So tolerance, how close to the rated value the part is, it'll be manufactured with a percentage variance. So for example, a carbon film resistor is typically 5%. So preferred values, so parts come in specific values from a series. The most common series is E24. The series are logarithmic and are based off rated tolerance. So pick values so do not overlap with each other. The E number denotes how many numbers the series has per decade. So when designing a circuit, the calculated component value will need to be rounded to the nearest preferred value. Stability, the change in component rating over time at a specific load, humidity level, stress, and ambient temperature. So changes in temperature and humidity cause physical stresses on components. So metal expanding or contracting due to temperature, insulation swelling, with humidity. Severe enough, it can destroy the part. So your power rating, the maximum power the component can dissipate at is rated ambient temperature without being damaged. Voltage rating is the maximum voltage above which the component will be degraded or damaged. Current rating, absolute maximum current the device can handle continuously without damage. So it's a lot of information. It's kind of not all that terribly exciting. So the instantaneous voltage VC across the charging capacitor is given by this equation. VC equals Vs 1 minus E to the power of negative T over RC. Cool. So where Vs is the supply voltage, R is the series resistance, C is capacitance, T is time since charging began in seconds. So if we have a 2200 microfarad capacitor connected to a 24 volt DC supply with 470 ohms of series resistance, calculate the voltage across the capacitor. After 1 second. So have a go at this calculation, take your time, and then we'll go through it. E stands for the exponential function, which is approximately 2.7182. Okay, let's see. I'm going to have to go through this one. Oh, yes. Okay, so what does this look like? Okay, hope everyone can see that. I don't know if it's back to front, but this is how you type in this equation to the calculator. So it's 24 bracket 1 minus bracket 2. Calculator issues. 2.7182 to the power of bracket and you have to put the brackets -1 over 470 times 2200 times 10 to the -6, because for micro, we need to move the decimal place 6 times, and then you'll need a bracket on the end of the exponent, and then another 2 brackets. That is how we write out this equation. Then we go equals, and we get 14.8754831. I know that probably looks backwards on the screen. Okay, that's good. As long as it's the right way for you guys. But I know that it's a complicated um, equation, but it's the kind of equation you guys will have to be able to work through. So how about you guys try typing that into your calculators and do it for 5 seconds. So all you need to do is change the -1 at the top of the exponent to a -5. There's the equation again. Might do. There we go. Nice and big. Yeah, once you've typed the equation into your calculator, it's really easy to go and change one value. So I'll let you guys have a go at it, and then I'll give you the answer. Oh, sweet. So I have taken a photo of my calculation there for that one and put it into the chat. So yeah, at 5 seconds, yep, 23.809 or 23.81. Yeah, so now we can go down and we'll have a look at 10 seconds. So if you still have the calculation still typed into your calculator, it should be real quick to change it. Yeah, so it is basically 24 volts at this time. Yeah, 23.998. But if you were to try and round that to two decimal places, it would put it up to 24 volts. Um, yeah, so this basically means that that capacitor is pretty much reached its charge point. So the voltage is at its peak. So it is. Um, so basically, it charges rapidly. So at 1 second, it was already at 21 volts. And now after 10 seconds, it's only reached 23, 24 volts. This is because it rapidly charges. It has a um, inverse, it's not exponential, pretty sure it's inverse charge characteristic. So it charges really quickly at the start and then it slows down as it gets towards full charge. So that is common with capacitors. It's the same with discharging. If we were to go backwards, if it was discharging, it would be the same. Cool. So BC337 is a common NPN power transistor with a gain HFE of 100. It is often used for driving small loads such as relay coils from the output pin of a microcontroller. Transistor acts as an amplifier. It controls a big current with a little current. When current is applied to the base, B, this allows current to flow between the collector C and the emitter E. The amount of current flowing through the collector IC will be equal to IB times HFE. So the amount of current will be equal to IB. So the current flowing in this portion here multiplied by the HFE, so multiplied by the gain. So emitter current IE here is the sum of IB and IC as per Kirchhoff's current law. These relationships can be written as HFE equals IC divided by IB and IE equals IC plus IB. Using this information, we can determine the output voltage of the circuit pictured. So calculate IB using Ohm's law. Assume there is a 1.2 volt drop from base to emitter of the transistor VBE. So if we have a volt drop between the base to emitter of the transistor, so here, if we have a 1.2 volt drop, that means we have 3.8 volts left for this circuit. So given we have a 1 kilo ohm resistor, how much current is going to flow in IB? So the current and the flowing through IB, so we use Ohm's law, I equals V divided by R. So we know we have 3.8 volts left. So how much current would we have if 3.8 volts flows through a 1 kilo ohm resistor? Yep. So that's in amps. What could we also express that as? Yep. We could express it as 3.8 milliamps. Just remember, guys, if someone's already posted the answer, please post one as well, just because it's how we do attendance most of the time, as we look at how much you guys have posted in the chat. Cool. So step 2, using the transistor's gain and the calculated base current IB, determine the maximum current that can flow from collector to the emitter. The amount of current flowing through the collector will be equal to IB times HFE. So what's the maximum current that can flow from collector to emitter? of IC, the current flowing through the collector, is equal to IB times HFE, or the gain, what would be the current coming through at IE? So and IE is equal to IC plus IB. Yeah. IC, what is the current that can flow from collector to emitter? IC. Yep. So the answer for step 2, using the transistor's gain and the calculated base current, IB, determine the maximum current that can flow from collector to emitter, which is IC. The maximum current that can flow from the collector to the emitter will be 380 milliamps, because 3.8 milliamps times, well, we know IC is IB times HFE. The gain is 100. Therefore, it must be 3.8 times 100, which gives us 380 milliamps. Now, step 3, now that we know IC, calculate the voltage drop across the resistor. Assume there is a 0.7 volt drop from the collector to emitter of the transistor when it is conducting current, VCE. So calculate the volt drop across the resistor. So there are 2 ways we can do this. What would be the volt drop across that resistance? Yes, so using Ohm's law, V equaling IR. That's all good, Oliver. You can always watch this again and kind of pause it and go over it. So yeah, by using V equals IR, we can multiply the resistance 3.3 by our current in amps. So we have to change it to 0.38 and we get 1.254 or 1.25 volts. So the last question, so B, so the circuit can be used to drive a relay by swapping the 3.3 ohm resistor of the coil of a 12-volt relay. But what extra component needed to be added to the circuit to protect the transistor from damage? That would be a diode. So we would add a diode in to protect the transistor from back EMF. But we will call it there for tonight, guys. I know it's the first week back, and some of you guys are potentially on block course. I'm not sure whether you are or not, or you're in the next couple of weeks. So we will call it there.